Welcome to Algebra 2, Semester 2, Unit 8. This is the first lesson in Unit 8. It is section 13.6 and sequences. We're going to start with the sequences first. But on page 1, you'll see the timeline. If you're missing class, make sure that you keep up with the videos and fill in the notes. And then you need to come in at lunch times before or after school to do the work with me and to make sure that you're getting beyond the concept that I just show online. In the vocabulary section, again, I've matched these up, so if you just list A, B, C, D, E, F, G down that side, they'll match up. Please practice a variety of different things and figure out what works best with your brain, whether you're doing flashcards or audio or whatever. Try some different things. You can get this. The main thing is you need to practice them about 10 to 15 minutes every single day during this unit. That's page 2, is the vocab. So moving on, we come to our sequences, and in the sequences, the very first one, if you look at that, it's 2, 4, 6, 8, and I'm asking you, what are the next two items? Well, probably you're used to just saying that, 2, 4, 6, 8, 10, 12, but what's really happening mathematically there is that you're adding 2 between each of those. When we add a number to get the next number, that's a recursive situation where you're adding 2 to the previous one. That is called an arithmetic sequence. And if you were to graph that, your first term being 2, so over here at 1, you'd be up at 2. Your second term, you're up at 4. You're going up a consistent amount on every single point, and so that ends up being a linear function. Arithmetic sequences, when you're adding, and arithmetic sequences end up being a linear function. You can actually come up with your equation, just knowing that that plus 2 is your slope, write that in front of your x, and then go backwards and figure out what the number is before the sequence starts. If I subtracted 2 there, the first number would be 0, so y equals 2x plus 0. That's an easy way to find your formula. If you're given a standardized test question asking for the formula on a sequence, remember that your x values are your term positions, so your x's would be 1, 2, 3, 4, 5, and your y's are your sequence numbers. And you can simply plug in your x value and your y value to find your formula out of a given list. So in class we might do a few of those just to practice for a standardized test. Next problem is not going to be adding. If you look at that, it goes 2, 4, 8, 16. So you ask yourself, well, what's the next number? How do I get from 2 to 4, 4 to 8, 8 to 16? If I were to add, I'd add 2 here, I'd add 4 there, I'd add 8 there. So you see a little bit of a pattern there, but it's not a recurring pattern with those same numbers. So the next thing I'd say is take these values and write them in a ratio and see if the ratios, with the right one over the left, right one over the left, right one over the left, and see if the ratios are all equal. In this particular situation, they end up equaling 2 over 1. So you know that this is being multiplied by 2. Because of a common ratio, they're being multiplied. So we'd multiply 16 by 2, get 32, 32 by 2, and get 64. This is called a geometric sequence. And if you were to graph it, the cool thing with this is you should be able to recognize the shape of this graph. Let's see if you do. Your first term is 2. Your second term is 4. Your third term is 8. It's over there at the third and fourth term that you really start to see the difference between it and this linear graph over here. The other thing is if you go back to the initial term here, divide 2 by 2, you get 1. So at 0, you're at 1. What kind of a function does that look like? Hopefully you remember, that is an exponential growth function. Most important that you just remember that's exponential. Geometric sequences are exponential. Now we're going to look at the different ways that you could write those rules on a geometric sequence. We have an explicit rule that we could use. Basically, this is whatever term you're trying to find, the term that you're looking for. This is your first term. And that R is our common ratio, which in the last problem up here was 2 over 1. So that's common ratio. And then this is the n from over there. It's the term that you're looking for. And so let's just play around with this. 64 we figured out for this sequence, and that's the 1, 2, 3, 4, 5, 6th term. So let's just verify that that should be 64 by using the formula. F to the 6th, meaning what's my 6th term? I take the first term and I multiply by the common ratio, and then that'll be 6 minus 1. Well, let's fill in. Our first term is 2. Our common ratio was 2. And 6 minus 1 is 5. So 2 to the 5th, 32, times 2 is 64. So we find that our 6th term is 64. Okay. Now, using a recursive rule basically says that your first term you just have to have, because you're building all of your future terms off of the previous terms. So the first term we just have to have, and the example above it was 2. Now to find the, this is your term looking for. F to the n minus 1 means previous term. R is our common ratio. So if we're looking for the 6th term, we're going to take our previous term, which would be our 5th term, and multiply it by 2. That's all that big formula says. So we take our previous term, that was 32. So F to the 6th is 32 times 2, which is 64. Okay, down here we have just a few practice problems with this. I give you another sequence. This is the bottom of page 3. We have 5, 10, 20, 40. If you look at this, it says, how do you determine the sequence is a geometric sequence? Hint R, meaning common ratio. So just write maybe check for common ratio. Now here in number 2 it says, using this technique, prove that it is a geometric sequence. So you take the term on the right and write it over the one on the left. So 10 over 5, then do it again, 20 over 10, do it again, 40 over 20. If those are all equal, then that is a geometric sequence. So 10 over 5 is equal to 2, 20 over 10 is equal to 2, and 40 over 20 is equal to 2. So it is. Now give the formula for the sequence. Well, let's say the formula for the 5th term. We kind of need to know a term number that we're going to go for with that. So if we look up there, looking for the 5th term, the explicit rule again was f to the n equals the first term times the ratio to the n minus 1. So the fifth term would be the first term, which is 5, times the common ratio, which we found was 2, to the 5 minus 1 is 4. 5 times 2 to the 4th is 16, equals 80. Now in the recursive rule, we have f1, which is just 5. Now we have f to the n, which we said fifth term, so f5, f4 times our r value. Okay, so f5 would equal our fourth term was 40 times the r value, which is 2, equals 80. So two different ways to get those. Okay, that's page 3. Turning over to page 4, at the top you are going to do number 4, 5, and 6 in class tomorrow in study groups. You can go ahead and look at it right now if you want, but let's work together on those tomorrow. OL means online. We're given a geometric sequence, has a common ratio of 5. You know that the sixth term is 30. How could you find the seventh term? Well, since we aren't given a first term, we don't want to use the explicit rule. So instead we'll go with the recursive rule. So looking for the seventh term, we're going to take the sixth term and multiply it by the ratio. So we plug in 30 for the sixth term, 5 for our common ratio, and we get 150 for our seventh term. Okay, you do need to write down all the formula and show how you're plugging things in. That's just showing your work at this level. So the next one, it says that the first term is 1 and we have a common ratio of 2. So this time we do want to use the explicit formula because we aren't given a recursive value and we're asked to find the 8th term. So we would put f to the 8 because we're looking for that 8th term. And then in the explicit rule, remember it is f to the first times your common ratio to the n minus 1, which would be 8 minus 1. So we just plug in our values that we're given now. The first term was 1, multiplied by the common ratio 2 to the 7th, which would end up equaling 1 times 2 to the 7th is 128. Okay, the rest of this page you'll be doing in class in your small study group. Let's turn to page 5. On page 5, you're actually doing clear down until you get to number 13, where it says real estate. The reason that I really like to teach you these sequences is it's really nice to be able to use them in real world application. This problem says real estate values are supposed to increase 5% per year. If you buy a house today for $100,000, what will it be worth in 4 years? Well, it's going to increase 5% per year. That means that at 100%, you're going to add 5%. So in actuality, the value next year compared to last year is 105%. This year it's at 100%, next year it's at 105. So to change that into decimal, divide by 100, we get 1.05. Now we can simply use our explicit formula. We have a starting amount, the $100,000 house, and we know the common ratio. It's going up by 1.05 per year. In 4 years, 4 minus 1, what will the value be? At this point, grab your phone, use the calculator, and pause the video and come back and see if you have the correct answer. Okay, I get $115,762.50 for the value of that house in 4 years. Okay. Now, another thing that happens in life is sometimes we have just common goods, everyday goods, groceries, that are predicted to increase at 4% per year. So again, that's 100 plus 4%. Now in class, I'm going to have you doing some decreases in values. Like we'll look at the value of a car that you might buy, and we'll look at the depreciation or the decrease in value. Now, I want to pose right now, if we're taking the increase and we're getting the R factor by taking the 100 plus 4%, what would you be doing with your 100% that it's worth today if it's going to decrease? So come into class prepared to discuss that with me. So we get 1.04 there. So in 10 years, we would have 3.20 times 1.04, 10 minus 1. So that's 3.2 times 1.04 to the 9th. Now I have to apologize, I don't have a calculator handy, and I forgot to do that before I got on the video, so would you please get that answer and check with me in class? I'll have it filled in by then. The last problem there you'll be doing in study groups. That's the end of page 5. Going over to page 6. The next thing that I want to do on here is just review the use of measures of central tendency and dispersion. Measures of central tendency, anytime you see that word, it is a phrase covering all three of our measures of what brings statistics to the center of a data, of the draw of data, which is our mean, our median, and our mode. Those simply represent where the middle of the data is lying. And hopefully you remember how to find those. We'll go over them briefly. Dispersion means how far apart values are dispersed. Another word for this would be range. Or you might see IQR, which is interquartile range. And we'll explain that real well here in just a little bit. Another word that we're going to get into here in just a little bit is standard deviation. I'm not going to put it on this quite yet because it's a little bit harder to explain, and I want to separate it out because I don't think you've probably dealt with standard deviation much. In fact, there is a video that I have put on your list that I did not film, but another person did, and it's just an excellent talk about standard deviation that you might enjoy, especially if you're headed into pre-calc and college classes. Please watch it. Okay, quiz scores are listed below. Which measures of central tendency best represent the set of data? Here's our data. Always put data in order, first thing, so that you don't forget. So we have 10, 10, 12, 13, 14, and 15. Okay. Now, in order to find the mean, realize now in high school and pre-calc, you're going to see mean represented by bar x. That's why I've put it in parentheses there. You start to get used to that. To find the mean, you're going to add all those and divide by the number there are. There's 6 values there. You just add between them. And I ended up getting 74 divided by 6, and I got 12 1/3. Please check out that you know how to do that. So 12.3 repeating for the mean. The median, as I put here in parentheses, is the middle number in an ordered list. So if we go to the middle, we see the middle is 3 numbers in. 3 numbers in is between 12 and 13. You can add those up and divide by 2, or you can just reason that 12 and a half is right between 12 and 13. You can write that as 12.5 as well. The mode is the most often occurring. That would be 10 because it's occurring twice. And now the range is your greatest minus your lowest, which would be 5. So the next thing that we want to look at is what will happen to the mean, median, mode, and range if we were to put an outlier in there. An outlier is a value that does not fit the rest of the data. It is 1.5 times your interquartile range away from the data. Since we haven't really discussed the interquartile range yet, just realize it's a value that's going to stand out. Just think of it as that for right now. Okay, so let's look at the median, mean, and mode and range and see how they differ with this outlier, that 30. 30 minus 10, 20. Obviously the range just increased significantly. Now the mean, if we add all these up, well, we had 74 before, so if we take 74 and we just add 30 to it, we get 104. This time we are dividing by 7. When we divide 104 by 7, I actually got about 14.9 rounded off. So the mean was influenced quite a bit. The mean actually increased. This is the bottom of page 6. 12.3 was what we had when we put the outlier in there. It increased by 2.6 values. These are pretty small numbers, so that's quite an influence. Over a 10% influence on the data. On the median, it doesn't really change the median as much, because if we go to the center, first we have to put them in order: 10, 10, 12, 13, 14, 15, and 30. If we go to the center of the data, we get 13. So the median was only influenced by 0.5. That's less than 10%. The mode wasn't influenced at all. If you look though, mode sometimes is not your best form of measure of central tendency, because as you see, 10 is clear down at the end. It doesn't really represent the data well. Now that we've got an outlier in there, the mean doesn't represent well either, because the mean's up at 14.9. That's at this end of the data. The one that really shows the best reflection of the data is your median. This is super important to remember for standardized tests especially, is that if there is an outlier, do not use the mean or average as a measure of central tendency. The preferred measure is usually the median. Preferred is usually median. Okay. Now we ask, what items are changed when we have a constant added to each value in the data set? Well, let's go back to our original data set from page 6. Our original data set was 10, 10, 12, 13, 14, and 15. So we're going to add a constant to all these. Let's just add, let me think about this, what would be an easy one? Let's just add 10 to each of them. So we get 20, 20, 22, 23, 24, 25. Our question is, how is that going to change the the mean, median, and mode. I can see that I'm going to run out of tape soon, so I'm going to leave you with that, come into class with that. The next problem here is what if we were to multiply each value? So let's take 10, 10, 12, 13, 14, and 15 and multiply each value. We have 20, 20, 24, 26, 28, and 30. Please fill in your mean, median, and mode and how those are changing before you come to class. We'll discuss that in class. And that is the end of this taping. Thank you very much.